So we're looking at a number of problems in energy transition related to, first of all, carbon storage, which is a key part of the whole energy transition. So capturing carbon dioxide from the atmosphere or from the emissions from a lot of industrial processes such as cement and iron and steel manufacture, and then taking that carbon dioxide and storing it in subsurface geological structures such as deep saline aquifers or depleted oil and gas fields, has the potential to accommodate up to about a quarter of the present emissions from fossil fuels. And the IPCC envisaged that in order to meet the 1.5 degree target, we need to be storing that volume of CO2 every year from 2050 to 2100. So understanding how CO2 travels through the subsurface and both the security and effectiveness of storing CO2 in these reservoirs is the centre point of a large part of our research. But we're also looking at problems of the environmental impact of deep sea mining. So the energy transition requires lots of minerals, and there's very large deposits of minerals on the seafloor, particularly in the Pacific. And there's a lot of interest at the moment in recovering those minerals. And we're looking at some of the environmental impact of removing minerals from the seabed and how the sediment associated with that will spread through the water column and redeposit over the seabed. So there's a very interesting set of challenges there to understand optimal ways of minimising that environmental impact. But we're looking at many other problems in energy transition. For example, we're looking at cooling of the batteries during electric vehicle charging. This is a key enabler to enable fast charging of electric batteries, and optimising that the cooling strategy is very important and a fundamental challenge in fluid mechanics. We're also looking at wind turbines and how we can align arrays of wind turbines to minimise the wake interaction on turbines downstream of other turbines so that we can optimise the performance of a whole array of turbines. And there's a lot of very interesting challenges in terms of maximising the efficiency of these wind turbine arrays. We're looking at the ways in which geologic formations develop and how the geologic strata are formed from deep sea sediment flows. And those flows enable us to understand how the geologic strata are formed. So if we're trying to look at the way in which carbon dioxide or hydrogen, which might be stored on the subsurface, flow through these deep rocks, we can actually build synthetic models consistent with the physics of how those formations were developed in the first place. So a lot of the work is on fluid mechanics of storing carbon dioxide and perhaps hydrogen for energy storage in geologic structures. The work we're doing on carbon storage can have an enormous impact on reaching the IPCC target. For example, the Net Zero Teesside project, which is planning to store carbon dioxide produced in an industrial cluster in the Humber and the Teesside regions, in a reservoir called the Endurance Reservoir in the North Sea, that will save carbon emissions equivalent to the emissions from 3 million houses. And so this carbon storage is an absolutely fundamental part of trying to achieve a net zero agenda by 2050. And our research is looking at some of the fundamental challenges of doing carbon storage, how we can safely store the CO2 in the subsurface. We can understand the risks and understand how to monitor that CO2 to check that it's safely stored, and understand some of the hazards and how we can manage those hazards, because that research then directly informs the industries who are involved in developing these schemes, who are trying to make sure that they're safe and reliable and they're optimising the resource. But also the research can help inform government, who are trying to form policy and regulation to accelerate the development of carbon storage. And globally, we need to ramp up our use of carbon storage by a factor of 100 or several hundred. And we've just written a report about this, which the government are presently digesting, a report by the Royal Society. And in that report, we've outlined, how we need to ramp up the deployment of carbon storage globally, and how it can become a leading industry in the UK because of the resource of porous rocks in the North Sea, which we could use to do some of this carbon storage. But it's absolutely fundamental to that the basic science we're doing is communicated to the industries and the other participants in this enterprise, so that the very best and most optimal approaches can be used to actually maximise the benefits of carbon storage. So geological structures and strata in the subsurface are very complicated. They're full of heterogeneities, layering and cross-bedding and other features, which means that predicting and modelling the way in which the carbon dioxide spreads is very complex. And this has a direct impact in how you determine the number of wells, the spacing of wells into which you're going to inject CO2. We're in very close dialogue with the companies who are developing these projects so that they can use the results of our research to help inform where to drill the wells and how to optimise the overall performance and maximise the potential of these systems, as well as ensure that the CO2 is stored safely. And ultimately, this is crucial because after some time, government will take over liability for the store, and demonstrating we understand how the CO2 spreads is absolutely critical for that. And so our research is directly informing some of those questions and that debate in very close collaboration with the different participants in this industry.